This is Chapter 1 in AP Chemistry, and this is Chemical Foundations. So this is a review of many of the things you were exposed to at the beginning of your chemistry class. So a definition of chemistry for you: it's the study of matter and the changes it undergoes. The chemistry that we study is not nuclear chemistry, but it's just the exchange of electrons. So two substances like chlorine and sodium can be poisonous to us, but once they react, it can form a substance that's quite necessary for us. The scientific method, remember, has three parts. You make observations, you form hypotheses, and then you perform experiments to test your hypotheses. In this micrograph, we have a benzene ring, so you can kind of see that. Remember, benzene is C6H6, so you can make out a ring structure. Remember that your basic units of measurement in the international system are kilograms, meters, seconds, the mole for amount of substance, and Kelvin temperature. Our prefixes, we can also say the value is the order of magnitude. And I gave you the Navy sheet is what I call it, that has all of these on it. So remember, you need to be able to remember some of these values. And as we do more and more questions, you can begin to see which ones you need to know and begin to memorize them. Let's use one of the prefixes in a conversion. And I would like you to convert 500 milligrams to grams. And if you look up what milli means, and my pen is way off, it equals, I've got to fix my pen. Let's see, I'm going to pause for a minute. I'll be right back. Okay, let's try this again. And we're going to take 500 milligrams and we're going to convert it to grams. Remember, milli equals times 10 to the negative 3. So we can also say there is 1,000 milligrams in 1 gram. So I prefer, in this problem, to use this conversion. So I'm going to take 500.0 milligrams, and I'm going to multiply by 1 gram divided by 1,000 grams. Milligrams, excuse me. Your milligrams cancel, and our final answer to the proper Sig Figs, 0.5000 grams. Let's look at another problem. Our next problem says convert 700 nanometers to meters. So nano means 10 to the minus 9th. Sorry, my pen's not oriented, but I'm going to keep working. So that means we can have 10 to the 9th nanometers in 1 meter. So to change nanometers to meters, we can take 700 nanometers and multiply by 1 meter is what we want. And I'm going to write 1 times 10 to the 9th nanometers in the denominator. Our nanometers cancel. And when you do your math, you're left with 7.00 times 10 to the negative 7th meters. Okay, so watch how that negative symbol, when you're saying how much of a nanometer, how much of a meter is a nanometer, you say 1 billionth, but then you can say there are a billion nanometers in a meter. Okay. Our last one is to convert grams to kilograms. Kilo means 10 to the third. So there are 1,000 grams in 1 kilogram. So on this one we have 8,905 grams. We're going to divide by 1,000 grams, and we're going to multiply by 1 kilogram. The grams cancel. You move your decimal, and we end up with 8.905 kilograms. Okay, let's look at uncertainty in measurement. And remember, when you read an instrument, you can read to the last graduation and then you can make a guess one place beyond that. So if you were reading this burette, you might say 20.15, but other people might have different measurements, just ever so slightly. Because the graduation is to 1/10 of a mil, you can guess to 1/100th of a milliliter. Those first 3 digits that have graduations are certain digits, and the last digit is your uncertain digit. So remember that significant figures automatically indicate that uncertainty in a measurement. So if you have 20.15 mils, it has 4 sig figs, and the last digit is usually assumed to be plus or minus 1. So in this measurement, we could say that 20.15 is plus or minus 0.01 milliliters. Whenever you measure, there's some uncertainty depending upon how the instrument is made and how many graduations are present. So if we look at this example, we have a soil sample and it's measured 15.00 grams in one measurement, and then the scientist uses a scale and says it measures 15. What is the difference between those two numbers? Well, remember, if you have 2 decimal places, you're saying you're plus or minus 0.01. So you know that your measurement is between 14.99 and 15.01. You're saying it's that good. Whereas if you say 15, you're going to say, well, it's between 14 grams and 16 grams. Much more uncertainty. So a quick review of precision and accuracy, and the old darts and target. Remember, precise is having all the same type of measurement, and accurate is having the acceptable measurement. So if you're throwing darts all over the board, you're not accurate and you're not precise. But if you can get them all in the same place, then we say it's a precise measurement in what we're talking about, but it's not very accurate because you want it in the bullseye. And if you get them all in the bullseye, you are precise as well as accurate. So when you look back at our measurements of the graduated cylinder, we can see that all those measurements are precise measurements. And we'd have to have an outside source to know if it was accurate. So an accuracy, how about if I say accuracy, depends upon the agreement of a particular value with a true value. Easy example is to think of a density of a metal. It is given, it has been tested by many different scientists, and you can compare your value to the accepted value. Precise or precision is just the degree of agreement among several measurements of the same quantity. How close are they? A quick Sig Fig review. Remember, for non-zero integers, they're always counted as significant figures. So here we have 4 Sig Figs, 3 Sig Figs, and 2 Sig Figs. Those zeros sometimes can give you trouble. Remember, if the zeros are leading, they're never significant. So looking at this number, you have 2, you have 2, and you have 3 Sig Figs. If the zeros are squished between 2 non-zero digits, so we call those captive zeros, they always count as significant digits. And this has 4, 3, and 4. If the zeros are at the end of a number, they're significant if a decimal is present. So if we look at the first number, there's 4, but 20 only has one sig fig. 4,000 has one significant figure. And when you use scientific notation, look at the mantissa, and that has 3 significant figures. Sometimes the Atlantic-Pacific rule helps you figure out how to count sig figs. Remember, the Pacific's on the left side of the continental U.S., and if the decimal is present, you count sig figs from the left. So we'd have 3 sig figs and 5 sig figs in those two numbers. If the decimal is absent, start from the right and count with the first non-zero digit. So 100 has 1 sig fig, and what do we have? 50,050 has 4 sig figs, the way it's written. If you have an exact number, you leave it out of your determination for significant figures. So exact numbers is when you're counting something, or it's a defined quantity. So say you have 10 apples. That's not a significant digit. If you have 1 inch equals 2.54 centimeters, that is a given number. A number in a formula, the R would be measured, but the 2 is an exact number. It would not be considered in sig figs. When you're multiplying and dividing, you always want to go to the least precise measurement, which means the one with the least number of sig figs. When you're adding and subtracting, you want to go to the number with the least number of decimal places. And so there's a couple of examples for you. Remember, when you round, you want to carry extra digits when you're doing your calculations until your final result. Don't round until you get to your final result. When you do round, if the digit to the right of the final significant figure is less than 5, then you keep the preceding digit the same. If your digit to the right of the final sig fig is 5 or greater, then you want to increase that digit by 1. So a couple of examples for you. So this is the end of the first part, and I'll put the next lecture on, I'll call it Chapter 1, Part B, or something like that. Okay.